Power and space are some of the biggest things to deal with in the data center, and they are usually 75% of the operational expenses of the data center budget. Google says that the power to operate servers costs more than the actual servers themselves. Interestingly enough, while bandwidth used to be essentially free in a data center, now bandwidth is scarce in the data center, and the network is becoming in the way, as noted by Amazon. So, why is power and space now become at the forefront of what we need to talk about? First of all, we know very clearly that the data center workload has changed. It used to be about enterprise applications, which were large and mostly internally focused. And now with the internet, everything's changed. The computing workload in today's data center is used by almost everybody in the organization. When you're dealing with cloud services, you could have millions of people connecting to a cloud service. Interestingly enough, most of these jobs are actually very small, simple, independent applications, which is a lot different than the past. They use huge amounts of bandwidth, and most importantly, the servers are often in very low utilization because they're built to scale on demand. And when servers are in low utilization and they're going to scale up, there's a lot of extra processor that isn't just not used, and they're usually anywhere between 5 and 20% loaded, even with the best virtualization technologies that are out there over the average of most web systems. With this change in workload, servers have completely failed to adapt. The architecture that's been out for well over 15 years has done nothing to really alleviate the power and space issues that we're seeing today. Traditional servers specifically are insufficient or inefficient at small, simple workloads, which is the majority of the workloads today. They're extremely inefficient when running low CPU utilization, which is the majority of the states that servers are in. And the issue is simply caused by the mismatch between this new workload and the architecture itself. So we set out to solve this problem, and along the way we had several different insights. One of the insights is around how many sockets you use in your servers. Sockets are where you put the central processing unit. What we found out is that if you use small single-socket CPUs, you have a 3 times advantage in terms of performance per watt over using large multi-socket CPUs, which is what you predominantly see in a legacy server. 3 times more efficient. It's a significant advantage to use single-socket CPUs. Of course, if you're going to attack the power problem in a server, you got to look at the CPU and the total power draw of the CPU. However, it turns out that the CPU is only about 1/3 of the total power consumed by the overall system. Everything else that is actually on the server motherboard, if you will, takes up the majority of the power. It's kind of startling. You would think that the engine of processing would be the thing that takes up the most power, but they've gotten pretty efficient, and it's really everything else that is taking up the majority of the power. So if we're going to solve the problem, you can't just get a more efficient CPU. You actually have to build a new architecture. So taking these insights, what we did is we produced a system that reduces power consumption by up to 75%, reduces the space by up to 85%, and increases the bandwidth by 12 times what's available today in a typical top-of-rack switch. It's based on a new system architecture, single box cluster compute. So we're talking about something that has got a lot of compute just in a single system. It happens to be independent of the CPU. Today we use x86 processors. We may use other instruction set processors in the future, such as ARM, which is, of course, what we see in most mobile platforms like your iPhone or Android phone today. We use the world's most efficient CPUs, small CPUs for the smaller workloads, and server class CPUs for large workloads. Then we invented virtualization technology at the hardware level that gets rid of 90% of the components that you find on a typical motherboard, leaving only the CPU, the memory, and our chip technology, our ASIC. Obviously, this shrinks the motherboard, eliminating power, cost, and space. We went further, and we have kind of a maniacal devotion to reducing power consumption in our systems. We actually turn off components of the CPU using our TO, or turn it off technology, that are not used. And when you're operating a server, a CPU is a general purpose computing engine. It often has things that are not necessary when operating as a server. We actually turn off that functionality, further optimizing the power used. And then to solve the bandwidth problem, we linked all of this together, all of these CPUs together with a supercompute fabric that solves both the bandwidth problem and also provides a method for us to dramatically scale out computing so we can build elastic compute infrastructures.